The multivariate chain rule will help us to determine how to compute partial derivatives from the composition of multivariable functions. Unlike functions of one variable, there are a lot of different potential setups, but for concreteness, let's work with the following situation. Suppose that w is a function of x and y, x is a function of s and t, and y is also a function of s and t. By plugging our value of x and y into the function for w, we get the following. So that now w has gone from depending on x and y to instead depending on s and t. And it makes sense to ask how w changes with respect to s and t, namely, what is the derivative of w with respect to these variables? To start, let's do an example without using the chain rule. Here are three functions mimicking the setup above, so let's compute dw ds. Immediately, we can just write w in terms of s and t like so. In this form, we can compute the partial of w with respect to s in our usual way, so let's do that. Pretending that t is a constant, we're forced to use our traditional single variable chain rule, and it's a little bit messy, but it's not impossible. With a bit of simplification, this is the answer we get. But the question we must now ask is how would we do this computation in terms of the various component functions? And there's a lot of reasons why we might want to do this. We might want to break the problem into smaller, more digestible pieces, or maybe one of the functions is like a black box. That is, we don't know what it looks like, but we can feed information in and out of it. The answer lies in tracing paths along a dependency tree, as I'll show you in a second. First, I'll write down our functions just so that we have them in sight. Then, starting with my topmost variable, I'm going to create a diagram where each new branch affects the variable above it. In this case, w depends on both x and y, so we'll draw out branches for this dependency. X and y both depend on s and t, so those get branches as well. And that's our dependency tree. Since the thing we're after is dw ds, we'll trace all paths from w to s. Right? These are the paths that start with w on top and end with an s on the bottom. Then we're going to add these paths together, writing the derivatives in the same order that we move down the paths. For this first path moving down the tree, we get dw dx, dx ds. We add this to the second path, dw dy, dy ds. And that's it. Right? We're done. But this notation can be a bit deceiving, so let me rewrite this now in terms of f, g, and h. And the important point to make here is that the dw dx, or df dx terms, are still evaluated at g of st and h of st. We note that this looks similar as well to the single variable chain rule, where we had to evaluate the outer derivative on the inner function, and it also ensures that our final answer is in terms of s and t instead of x and y. To see this at work, let's redo our previous example, but this time we're going to use the chain rule. We can see what we need at the top of the screen, so let's compute that set of derivatives. We start with dw dx, which isn't too bad. And since we'll need our answer in terms of s and t, let's plug in what x and y are now. dw dy starts off exactly the same way as dw dx, but changes once we plug in s and t. Finally, dx ds and dy ds can be done pretty quickly as well. Using our formula, we multiply and add these together to get the following. With a bit of simplification, these can be combined so that our answer is this, which is exactly what we found before. So by using the dependency tree, we can break these complicated derivative computations into smaller pieces.